किने टाटू किने लगा बस आ गया बस चल रहा है
ऑटोमेटा को हम यूज करते हैं रेगुलर लैंग्वेजेस के लिए, और डीसीएफएल और सीएफएल के लिए हम यूज करते हैं पुश डाउन ऑटोमेटा। तो जब भी हम बात करते हैं यहां पे इनकी पावर की, तो फाइनाइट ऑटोमेटा इज हैविंग अ लिमिटेड पावर, मतलब कोई कंपैरिजन वाली लैंग्वेज नहीं होनी चाहिए और कोई भी नॉन लीनियर पावर वाली नहीं होनी चाहिए, लीनियर पावर हो और कंपैरिजन वहां पे नहीं होना चाहिए। और ऐसे अगर हम बात करें पुश डाउन ऑटोमेटा की, तो लाइक हेलो दोस्तों, गेट्स पहले हमने डिस्कस किया है फाइनाइट ऑटोमेटा को और इवन पुश डाउन ऑटोमेटा को, जो कि हम यूज करते हैं। लाइक फाइनाइट ऑटोमेटा को हम यूज करते हैं रेगुलर लैंग्वेजेस के लिए, और डीसीएफएल और सीएफएल के लिए हम यूज करते हैं पुश डाउन ऑटोमेटा। तो जब भी हम बात करते हैं यहां पे इनकी पावर की, तो फाइनाइट ऑटोमेटा इज हैविंग अ लिमिटेड पावर, मतलब कोई कंपैरिजन वाली लैंग्वेज नहीं होनी चाहिए और कोई भी नॉन लीनियर पावर वाली नहीं होनी चाहिए। लीनियर पावर हो और कंपैरिजन वहां पे नहीं होना चाहिए। और ऐसे अगर हम बात करें पुश डाउन ऑटोमेटा की, तो लाइक अगर हमारे पास लैंग्वेज आती है ए पावर एन बी पावर एन, जहां पे नंबर ऑफ कंपैरिजन कितने हैं, एक, जैसे ए और बी क्या होना चाहिए, बराबर। तो इस टाइप की लैंग्वेजेस के लिए हम यूज करते हैं पुश डाउन ऑटोमेटा। इवन कैसे हम डिजाइन करते हैं ये सारा जो ऑलरेडी मैंने इसके ऊपर वीडियोस बनाई हुई है, फाइनाइट ऑटोमेटा के ऊपर भी ऑलरेडी वीडियोस हमने सारी बनाई हुई है, तो आप वो वीडियो जरूर चेक करें, क्योंकि इसके ऊपर काफी कॉम्पिटिटिव एग्जाम में, इवन आपके कॉलेज यूनिवर्सिटी में भी उसके ऊपर क्वेश्चन पूछे जा सकते हैं। अब हम बात करते हैं यहाँ पे ट्यूरिंग मशीन की पावर की। तो ट्यूरिंग मशीन जो फाइनाइट ऑटोमेटा एक्सेप्ट कर रही है, मतलब रेगुलर लैंग्वेजेस के लिए और डीसीएफएल सीएफएल के लिए तो एक्सेप्ट हो ही रहा है, मतलब उनके लिए तो वो यूज कर ही सकते हैं। लेकिन अगर हमारे पास लैंग्वेजेस आती है लाइक दिस, ए पावर एन बी पावर एन सी पावर एन। हेलो दोस्तों, गेट्स मैसेज में आपका स्वागत है। इस वीडियो में मैं
आज हम लोग देखेंगे ऑटोमेटा का यूनिट 4, जिसमें है ट्यूरिंग मशीन। इसमें ज़्यादा तो ये जो यूनिट है ना, ये यूनिट 3 और यूनिट 2 के कंपैरिजन में थोड़ा इजी है और ज़्यादा न्यूमेरिकल्स में नहीं है। मतलब टॉपिक जो है ना बहुत कम है। मेनली इसमें कंस्ट्रक्शन ही है, मेनली हम लोग के पास थ्योरी मतलब न्यूमेरिकल पोर्शन में। तो सबसे पहले देखते हैं कि ट्यूरिंग मशीन में हम लोग के पास ना जरूरत ही क्यों पड़ा, जब पीडीए जो था ना पुश डाउन ऑटोमेटा था, तो ट्यूरिंग मशीन का हम लोग के पास क्या जरूरत था। तो पीडीए में ना हम लोग क्या करते थे, हम लोग पुश डाउन ऑटोमेटा में स्टैक का यूज़ करते थे। स्टैक में कौन कौन से ऑपरेशन हम लोग यूज़ करते थे, तो पुश और पॉप का हम लोग यूज़ करते थे पीडीए में। ये जो ट्यूरिंग मशीन है ना, इसमें हम लोग पुश और पॉप का यूज़ नहीं करते हैं। इसके बदले हम लोग क्या करते हैं, तो रीड राइट ऑपरेशन का यूज़ करते हैं, जो बेसिकली कर स्टार्ट हुआ। स्टार्ट यहाँ से हो रहा है, तो हम लोग डाटा आज हम लोग देखेंगे ऑटोमेटा का यूनिट 4, जिसमें है ट्यूरिंग मशीन। इसमें ज़्यादा मतलब ये जो यूनिट है ना, ये यूनिट 3 और यूनिट 2 के कंपैरिजन में थोड़ा इजी है और ज़्यादा न्यूमेरिकल्स में नहीं है। मतलब टॉपिक जो है ना बहुत कम है। मेनली इसमें कंस्ट्रक्शन ही है, मेनली हम लोग के पास थ्योरी मतलब न्यूमेरिकल पोर्शन में। तो सबसे पहले देखते हैं कि ट्यूरिंग मशीन में हम लोग के पास ना जरूरत ही क्यों पड़ा, जब पीडीए जो था ना पुश डाउन ऑटोमेटा था, तो ट्यूरिंग मशीन का हम लोग के पास क्या जरूरत था। पीडीए में ना हम लोग क्या करते थे, हम लोग पुश डाउन ऑटोमेटा में स्टैक का यूज़ करते थे। स्टैक में कौन कौन से ऑपरेशन हम लोग यूज़ करते थे, तो पुश और पॉप का हम लोग यूज़ करते थे पीडीए में।
Hello. Hello. Pick it up, bro. இப்போ நான் ரிமூவ் பண்றேன். ஓகே.
Hello everyone. This session we are going to see introduction of a new mathematical model, that is Turing machine. Turing machine is a mathematical model of automata theory. It is like a finite automata with an infinite tape as a memory unit. Okay, so here Turing machine has an infinite tape as a memory unit. In tape, it is splitted into small cells. Each cell is capable of storing a single input at a time, single alphabet at a time. It might be either A or X or Y or something. Each cell is capable of storing an alphabet at a time, and this is infinite, and we have a read-write head that focuses on the first element. For our consideration, we are going to consider this leftmost side of this tape to be sealed, and whenever we are starting the process in a Turing machine, the input is returned from left to right in the Turing machine, this tape. Okay, and we have a read-write head. Read-write head. This head is capable of reading the element in a tape, and it is capable of erasing it and write a new element in the tape. And here it is a movable head. It can move either left or right a step. Each and every time when you want to make a transition, it just move one step ahead. Either left or right, it just move one step at a time. Okay, and the process always starts with this transition starts with this Q0. And in tape, whenever we start the Turing machine, input is written from left to right, and remaining left out portion of the tape will be considered as blank symbol. We use symbols B. represent the blankness of the tape. This tape is infinite. So we have some remaining free spaces in the tape. In order to denote the free spaces of the tape, we are going to use some symbols, like blank can be represented as either B, or we can use this hash symbol, or just a symbol like this, or a single hyphen. All the symbols are used to represent the blank spaces. So it is up to the user to take the symbols it is up to the user's choice. Now here we have a finite control in Turing machine. We have a finite control from where this read-write head is attached. This finite control contains the programs or the transition, that whatever we have discussed, that will be there in this finite control, and based on the transition function, the read-write head is capable of moving left or right at that time. Okay, so now the important thing in this Turing machine is here we have a special acceptance state. Like as usual, we know Q0 is the starting state of automata, and we are having a special final states, that is Q accept and Q reject. Q accept and Q reject are the two final states that is described in this Turing machine. Whenever a transition enters into Q accept, the input will be accepted. Whenever the transition enters into Q reject, the input will be rejected. Okay, so the language acceptance of a Turing machine is whenever the transition of Turing machine enters to the accepting state, the language is accepted. There is no at the end of input points and all. In case of push down automata, what happened? Both in case of push down automata and finite automata, whenever a language is set to be accepted, like we have to process all the input symbol. Only at the end of input, if the transition moves to the final state, we say that the input is accepted. But here there is no constraint regarding this. Whenever at the time of transition, if a Turing machine entered into the Q accept state, the input will be accepted. Okay, so each and every step move of a Turing machine can be described as each step move of a Turing machine is based on this current state and tape symbol at the given portion, tape state and based on this current state and tape symbol at the given portion, what is there in the tape? This will be the current tape symbol and the current state. Whatever is the current state, we are going to write a new symbol on the tape. So based on current state and current tape symbol, we are going to write a new symbol on the tape, and we are going to make a left or right side move. Make a left or right side move, and then we are going to go for a new state. So each step transition of a Turing machine is based on the current state and the current symbol on the tape. We are going to write a new symbol instead of this symbol, and we are going to make a left or right side move, and then we are going to make a state change. So this we can make a left or right side move, and then you're going to make a state change. So this we can call it as either move of a Turing machine or transition of a Turing machine. This can be symbolically given as transition of q comma a is equal to p comma b comma l r y. Here q is the current state, A is the current tape symbol, and P is the next state that we want to move, and B is the new and is the current state. A comma L R Y. Here Q is the current state, A is the current tape symbol, and P is the next state that we want to move, and B is the new symbol that we are going to write in the tape instead of this move, and B is the new symbol that we are going to write in the tape instead of this A, and is the new symbol that we are going to write in the tape instead of this A. And LRR is the left or right side move. Okay, so this is how a transition in a Turing machine can be given. So now the formal representation of Turing machine can be given as the formal notation of a Turing machine can be given as Turing machine is equal to Q epsilon tau del Q naught B and F, where Q is finite set of state and epsilon is the input symbol. Turing machine is equal to Q epsilon tau del Q naught B and F, where Q is finite set of state and epsilon is the input symbol, and tau is used to represent the symbols that can be written on tape. Okay, there are only few symbols that can be written on the tape, so this tau represent the tape symbols, and del is a transition function. That is what we have discussed earlier. So del can be given as q comma a is equal to p comma b comma l bar r. So this L bar R is up to the user, like it is based on the function. You have to take either L or R. Okay, only one movement at a time. It may either move left or right side once. And Q naught is a starting state. And B is the symbol that is used to represent the blank spaces. I told you like Turing machine contains infinite tape as a memory unit. The free spaces in the Turing machine are represented using the blank symbol. Here we have taken B as the blank symbol. Here we have taken B as the blank. And B is the symbol that is used to represent the blank spaces. I told you like Turing machine contains infinite tape as a memory unit. The free spaces in the Turing machine are represented using the blank symbol. Here we have taken B as the blank symbol. State, set of final states. As I told you, the set of final states here are Q accept and Q reject. Turing machine always have two special accepting states. It might be either Q accept or Q reject. Whenever the input want to be accepted, Turing machine goes to accepting state, or else it goes to this rejection state. So this is the formal notation for a Turing machine, formal way of representation of a Turing machine. Now we'll see a problem of a Turing machine, a very simple problem of a Turing machine. Consider a very simple example for Turing machine. Here we have taken a language acceptance problem of a Turing machine. We are going to construct a Turing machine that accepts the language over the alphabet A comma B. So the input here are made up of A and B combination, and that contains all the strings that end with B. Okay, so this is a condition that we are going to focus on. The input string here is made up of A and B that always ends with B. Okay, we'll just consider some example here. And the input is just B, it ends with B. When it is AB, it ends with B. BB, it ends with B. AAB. In all the cases, if the input string ends with B and we have a combination of it, then these are the strings that the Turing machine has to go to an accepting state. Okay, so now we want to construct a Turing machine for a problem of this kind. State machine, a very example going to focus on. The input string here is made up of A and B that always ends with B. Okay, we'll just consider some example here. And the input is just B, it ends with B. When it is AB, it ends with B. BB, it ends with B. AAB. In all the cases, if the input string ends with B and we have a combination of it, then these are the strings that the Turing machine has to go to an accepting state. Okay, so now we want to construct a Turing machine for a problem of this kind. Okay, so input here is random. You are going to, like whenever a Turing machine is started, the tape will contain the input. Whatever might be the input, the input is written from left to right. And this leftmost symbol will be focused with this read write head with the starting state Q0. Okay, and you have some random input, and as per our condition, the input end with B, and the remaining tape symbols, the left out portion of the tape are represented using this blank symbols. Okay, so now whenever the input end with B, the Turing machine has to go to accepting state. Okay, so the basic idea of it is in Q0 we can have a transition. Okay, so input centered using this blank symbols. Okay, so now whenever the input end with B, the Turing machine has to go to accepting state. Okay, so the basic idea of it is in Q0 we can have a transition till the end. Since we want to know about this last element, we have to move till this blank symbol. Okay, so in Q0 we can have a transition. In Q0 is the starting state. We can have a loop. The input is made up of the combination of A and B. So for all possible combination of A and B, we just have a transition. We just keep on moving right. And in order to denote the last element, we have to move till this blank. Whenever it is a blank, the prior element will be the last element. So we have to move till this blank. And once we found a blank, we have to make a left side move. So once we found a blank symbol in the Q0 state, we have to make a left side move. So here the blank symbol in the tape will remain as it is. There is no change that we make over here. So the blank symbol will remain as it is, and we are just making a left side move to a new state Q1. In the state Q1, if the input is B, it means that the input ends with the string that we have taken. The blank, we have to make a 11. So we have to move till this blank, and once we found a blank, we have to make a left side move. So once we found a blank symbol in the Q0 state, we have to make a left side move. So here the blank symbol in the tape will remain as it is. There is no change that we make over here. So the blank symbol will remain as it is, and we are just making a left side move to a new state Q1. In the state Q1, if the input is B, it means that the input ends with the string that we have taken ends with B. So if the input ends with B, we are going for this Q except state. A very simple problem of Turing machine. This B will remain as it is and we are just making a right side move. So after going to this accepting state, this right or left side move doesn't matter. Okay. So this is a very simple problem that accepts all string that ends with B. The basic idea is for all the n number of strings, we just keep on moving right, and when we come to the end of the string, ns is denoted using this blank symbol. Once we reach this blank symbol, we are going to make a left side move, a simple left side move, and we are going to make a state change to this Q1. In Q1, if the input is blank, it means that the last element is B. Sorry, input is B, the last element is B, we are going for this accepting state. Okay. So now we'll consider an tape structure for example. In order to make check the working of this input, we consider an example W is equal to ABB. Okay, so this tape, whenever we start a transition, tape contains all the element A, B, P written on the tape, and the remaining left out space will be the blank symbol. While starting the transition, read write head focus to the first element and we start the transition with the starting state. Now Q note when the input is A. For all the cases when the input is A or B, we just keep on moving right. So here first we just make a right side move, and again we make a right side move. So we have to keep on moving right when no matter whether the input is either A or B, we just keep on moving right. Now when we found a blank symbol in Q naught state, when we found a blank symbol, we have to convert that, we have to keep the blank as it is, but we have to make a left side move to the state Q1. Now we have a state change over here. In Q naught, when the input is blank, we have to make a left side move to the state Q1. In this state, we are going to make a left side move to the state Q1. Now, in Q1, if the input is blank, we are going for this accepting state. Okay, finally, in Q1, if the input is B, then we are going to make either right or left side move and we are going for Q except state. This is this tape structure. This diagram we call it as tape diagram. Each and every step describe the tape structure at a time. Okay, and this can be each and every step describe the tape structure at a time. Input is B, then we are going to make either right or left side move and we are going for Q except state. This is this tape structure. This diagram we call it as tape diagram. Each and every step describe the tape structure at a time. Okay, and this can be formally represented as instantaneous description or ID description. Here, the tape structure can be written as it is, and whenever instantaneous description. Instantaneous description. Instantaneous description is at a point the representation of entire transition. Okay, so now wherever this read write head focus on, before that we have to mention the state. Okay, it focuses on A, so before A I just write the state Q naught and the remaining tape symbol as it is. So this is your first instantaneous description, and next we have this. Here the instantaneous description is given as A, and here we have this read write head focus. So in before A we have to write Q naught, B, 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 and here we have A, B, and here we have this read write head focus on, so we have to write the Q naught over here, B, B, and for this step it is A, B, B, and here before this Q naught, B, and similarly for this step A, B, and here we have the rewrite head, write Q1, B, B, and for the last step, it is A, B, B, Q except B. Q except B. So these are all the instantaneous description, and as a whole, when you write the transitions using this instantaneous description, you have to write it over here. This is the first step, and the second step is from this step we got A Q naught B B B, and from this step we got this. When you want to club 2 or 3 steps together, I can use the star symbol. On 2 or 3 transition, I got A B B Q naught B. Here I have skipped this step, so I use the star symbol. Okay, and here it's A B Q1 B B, and thank you.
Hello everyone. The different ways in we can represent Turing machine. Okay, different ways in which a Turing machine can be represented. One simple example, I'll show you how to construct a Turing machine for it. Okay, so you know what is Turing machine, right? Turing machine is a mathematical model, and that is going to have an infinite tape as a memory unit. Okay, a tape with infinite length, and this tape is split into cells. So you will have a lot of cells in between. Cell is actually meant to be a small space, and you have a read-write head focusing on the first cell. So each cell is capable of storing one alphabet at a time. So if I take my input as an A-B combination, one cell I can write either A or B, one alphabet at a time. And similarly, if my input is of a binary element, I can write either 0 or 1 in each and every space. Okay, so now this is the usual constraint, and we start with the starting state of Q naught. And when can we call a Turing machine is, when can, like language acceptance of a Turing machine, when can we say that the input is accepted by Turing machine or not? Or not? Or not? Machine or not? Starting state of Q naught. And when can we call a So whenever a Turing machine enter into an accepting state, the input is accepted, and whenever it enter into a rejection state, the input is rejected. Okay, so we have a special acceptance state over here, and whenever a Turing machine enter into it, we say that the input is accepted. Okay, so this is the constraint. We are not going to go end of your input like your NFA, DFA or a PDA. Okay, what happened with NFA, DFA, push down automator? We just go start from the starting alphabet of the input till the end of the input, and after reaching the end of the input, we say that the input is accepted or not. Over here, in case of a Turing machine, whenever this transition state enter into a accepting state, the input is accepted. I'll show you an example for it or not. Over here, in case of a Turing machine, whenever this transition state enter into a accepting state, the input is accepted. I'll show you an example for it. Let us consider this language over the alphabet A comma B. So my input consists of all the combination of A and B, and whenever input start with ABB, I have to accept it. Okay, if the initial elements are A, B, B, we are going to accept the input. And it is like programming here. See, all these, whatever we are going to construct over here, it is similar to a C program or a C++ or Java program. So, logic may vary from person to person, and the way in which they write a coding or a logical values for it, it differs. Okay, I am not going to say that whatever I am going to write here is going to be the standard one. You can logically think about it and write it in a different pattern too. Okay, so one such a way is my input should start with ABB. This is a very simple procedure. I can just have the input in my tape. See, I told you now, like whenever we start the Turing machine, you have to take this input. If my input is ABBA, this is my input. Whenever a Turing machine is started, this input is written in the tape as ABBA, one alphabet in a cell, and followed by the blank representation. We have used Z0 to represent the bottom element of stacking push down automator, right? Similarly, to represent the blank symbols, we use this symbol. Either we use this blank representation or we use this hyphen as a representation. Okay, it is up to the user to decide on. I use the capital letter B to denote that this is the last empty spaces. Okay, and the transition will be in the starting state Q0 representing the first element. This is read write take. It is able to look into the place of the cell and read what content is there, and it has the possibility of erasing it and writing it a new content into it if needed into it. Okay, so my case is the input should start with ABB. So whenever input start with ABB, we are going to accept the input. So one way I can start is in Q0. If my input first element is A, it is in proper structure. I check the next element. Okay, so I can draw the transition diagram like this. So we have a Q0. Element is A. It is in proper structure. I check the next element. Okay, so I can draw the transition diagram like this. So we have a Q0, a starting state. Starting state focus on the first element. If my first element is A, it is in proper structure. I make a move to Q1 state. I am not replacing anything. Over here. The tape will remain as it is. We don't want to replace it. So A will remain as it is. I make a move to the next element. So next element should be B. Right? So if the next element is B, I make a transition like what we have done for your NFA or DFA, the same structure. First element should be A. Got it? And next element should be B. So BB, move right. And the next element should be If the next element is also B, we are going for acceptance state. We are going to accept the input. I told you the input should start with A, B, B, then you are going to accept the input. Now clearly for Q naught, read the first element. If it is A, make a transition to the next state. Move right. So the read write head will move from this place to this place. I'll draw the tape structure. So first element is A, B, B, A. The tape remain as it is. If the first element is A, I make a right side move to Q1 state. And what is the next step? Next step is in Q1, if the input is B, the B remains as it is. I just make one step right to this one, and Q1 when the input is B, I make a transition to Q2, and Q2 when the input is B, the input starts with ABB. It is in proper order, so we can go for an acceptance criteria over here. So the last step here is I can draw a transition like this: A, B, B, A. The transition, once we are going for an acceptance state, we can either move right or left, it doesn't matter. So since I have written it as a right side move, I am writing a transition like this. So Q2 when the input is B, we are going for Q acceptance state, and whenever your transition enters into Q acceptance state, your Turing machine stops. Okay, so this is the transition tape structure and this is your transition diagram. And we exactly here know that when you are input will be rejected. The input should exactly start with A, B, B. If it is not starting with A, B, B, we can have a rejection statement. See here, I can write Q reject here. And when I exactly know that if the input first element is B instead of A, I can reject the input. Or if my next element is in Q1, I want a B, but instead of a B, if I have a, I can reject it. And similarly in Q2, I need a B, right? Input should start with A, B, B. If it, so rejection is also allowed over here, a special rejection state where whenever you, okay. So this is a complete representation of a Turing machine when the input is of the combination of A and B, and see here we haven't checked the last element. We haven't reached the end of the input. We just check first three element. If the first three element is A, B, B, we are going to accept it. That is the difference between a Turing machine and your other mathematical models. Other mathematical models have to wait for acceptance till we reach end of the input. But we don't care about it. Whatever is needed, we just scan that, and if it is existing, we just process it. Okay. So now this representation we call it as transition diagram. Transition diagram, and this way of representation is called tape representation. Tape representation is something like it denotes step by step how your tape structure looks like. Okay, and there is one more thing called instantaneous description, like you have it for NFA, DFA and push-down automata. So instantaneous description is something at the instant how your input, how your process looks like. Okay, so you have a state and you have a tape structure and you have a read write head. So we have to write all those things together. We have to merge all those things together. So wherever you have this state, you have to the prefix of it. You have to for instant to transition table, a transition table, a Turing machine. So one is representation, so two more specific representation when it comes to a Turing machine. So one is called the Q accept of a blank blank. So this is called instantaneous description. I description writing it over here in the structure. So we saw what is a tape representation, what is instantaneous description, and what is the transition diagram. And you have one more specific representation, so two more specific representation when it comes to a Turing machine. So one is called the transition table. So you remember what is a transition table? A transition table is something you have it like this. We have done it for a transition table for your NFA, DFA, but we haven't done for push-down automata. Okay, the reason is see in your, okay, but we haven't done for push down automata. Okay, the reason is, see in your transition table, in one side we have all the states. Your states here are Q0, Q1, Q2, Q accept and Q reject state. Okay, and your transition is based on, each step your transition is based on the element that is written on the tape. Okay, so you can write the tape elements over here. Here my inputs are going to be A and B. The element that is written in the tape is also A and B. So for A and B, I am going to write the transition. All the states on the element that is there in the tape, you are going to write the transition. One example is Q0, when the input is A, it goes to Q1 with A as it is. Okay, so it has the A in the tape as it is and make a right side move, making a transition to Q1 state. So this is how you have to write the transition. Okay, so the transition has to be written like Q0, when the input is A remains as it is, move right to Q1 state. And Q0, when the input, the transition has to be written like Q0, when the input is A remains as it is, move right to Q1 state. And Q0, when the input is B, it goes to Q reject state and B remains as it is and move right. Okay, a table represents state, and Q2, when the input is B, goes to Q accept state. Q accept and B remain as it is, move right. And for Q acceptance, you don't have any transition. Q rejection also, you don't have any transition. Okay, so this is your transition table representation. Okay, so transition table representation is something you have to put up in a table structure. So this transition table is applicable only for NFE, DFA and the Turing machine. We cannot apply this in your push-down automata, since the transition in push-down automata is based on the state, input and the element that is there in the tape. So it is three-dimensional thing that cannot be represented in a two-dimensional transition table. So in Turing machine, the transition is really based on the current state and the element that is written in the tape, so we can write it like this. Okay. So now the last representation, a very important representation, is called a formal way tuple rotation. How formally you are going to represent your Turing machine? So you have this, right? Q sigma transition, the element that can be written in the tape, Q naught the starting state and F is your final state. And over F you have two possibility, you have Q acceptance and Q rejection state. So these are all the tuple notation for a Turing machine. Q is finite set of states. For this example it is Q naught, Q1, Q2, Q accept and Q reject. And sigma is the input elements. Your input is based on A and B. So sigma is A and B. Then is the transition function. You can write your transition function like this. Transition of Q naught, when the input is A, it makes a transition to Q1 state by replacing A by A and making the right input elements. Your input is based on A and B. So sigma is the input. Example it is Q naught, Q1, Q2, Q is finite set of states. For this example it is Q naught, Q1, Q2, Q accept and Q reject. And sigma is the input elements. Your input is based on A and B. So sigma is A and B. Then is the transition function. You can write your transition function like this. Transition of Q naught, when the input is A, it makes a transition to Q1 state by replacing A by A and making the right side move. Okay, so this is one single step of transitions. So Q naught on the element that is there on the tape, it make a move to the next state. So A remains as it is and we are making a right side move. So all this transition that we have taken over here, right, that can be put up in a structure like this. And this term is the transition function. See here I forget to write, you have a blank symbol representation too. When you are writing a transition table, over the tape element consists of input A and B followed by the blank symbols. So these symbols are also there in the tape, right? So you have to write the transition for that also. Since here it is all null, I haven't noted it down, but make sure you are writing it. Okay, so here the element that can be written in the tape is input element along with the blank representation. And Q naught is my starting state, Q accept state, and I have a special rejection state as Q rejection state. Okay, so this is a complete Turing machine representation for one example that I have taken. So what are the representation we have? Transition diagram, transition table, tuple notation, tape representation for showing your input is correct or not, to simulating an input, and you have this instantaneous description. Okay, so the example that I have taken is very simple. I'll take one more example and I'll show you how it is exactly working for all the representation. So let us take one example where my input is going to end with something. Okay, we know how to construct a Turing machine when it starts with something. Now instead of starting with AB, I'm going to accept all the input if it end with AB. Okay, so I'm going to construct a Turing machine. Whenever my input end with AB, I have to accept it. Okay, so this is very simple, but you have to write the transition over here. If my input W consists of ABB, AB, B. Okay, if this is my input, my ending should be AB. That is the constraint. Okay, so how can thingy? So like the language that I have taken is a regular language. So I'm able to construct NFEDFE or like a finite automata or even a Postman automata or even a Turing machine. See, your language representation goes like this based on your Chomsky hierarchy. So whenever a language is regular or a context free or a context sensitive or an unrestricted language, we can construct a Turing machine for it. It covers up everything. So whatever the problem that we have discussed so far, we can construct a Turing machine. That's why I told you, whenever a language is solvable, okay, whenever a problem you say that it is solvable by a computer, then we can create a Turing machine for it. Okay, a Turing machine is a common representation for all this. Okay, so coming to this problem, I can do any way, like your finite automata or something. One simple way is I can put a loop to reach my blank symbol, and I can just move one step left to check the last two elements. Okay, so how can you do it? I can draw a transition diagram like this. I can have a state of Q0, the starting state, where I just read each and every input until I reach a blank symbol. So I put a loop when the input is A or when the input is B, I keep on moving until reach the blank symbol. And the left side move, making a transition to Q2 state. Okay, from here on the thing is easy, right? When I reach the last element blank, okay, from here on the thing is easy, right? When I reach the last element blank, and I am going to check what is there in the left side of it. One step prior, if the input is B, the input should end with AB, right? If the last element is B, it is in proper structure. I am going to make one more left side move to Q3, and here I am going to check if the element is A. If the input is A, we are going for a Q acceptance state. Okay, so the same case as in the previous one, but rather than checking the first two elements, I am going to check the last two elements. So when I am checking the last two elements, reach till the blank symbol, go one step left. If the input is B, make a transition to Q3. In Q3, if the input is A, your element, reach till the blank symbol, go one step left.
ওই করি ভাল লাগে আয়ো और खिलाओ और खिलाओ लगाया होगी। क्या के खाना खाता है? अच्छा
If the
देखो
input is B, make a
क्या है किधर पीछे आंखें मिलाया अब छन दिया पूजा दीदी हाथ कर इसको क्या पैकिंग करके दिया जमाई दिखाई दिखाइयो ये क्या पैकिंग करके दिया है जमाई बोल दो बेटा जल्दी है मां बोल दो आदमी हाँ और देंगे तो वो ये आग लगा लो पंजरा लावायची. पाच
transition to Q3. A, you're going for an acceptance state. You can move left or right, that doesn't matter once you are reaching your acceptance state. And what will
How's it going, everyone? John here. Graded not here, but that's fine if you want. What you're going to want to do is click on the three dots, and you're going to do. And what we're going to want to do is set up a custom doc, which I already have set up. But what you're going to want to do is go up to View, Docs, Custom Browser Docs. And as you can see, I already have one set up. So you're just going to give it a name. And then you're going to Control V to paste it and hit apply. So what that's going to do is that's going to then populate that right here, just like how you see mine. Since I already had it set up, it didn't go and populate it, but it was already there. Now what we need to do is take this and bring it over here into... How's it going, everyone? John here with Graded YouTube, and you're going to want to open up one of your streams. And you can see your chat here, but that's fine if you want to look at your chat here, or if you want to look at chat here, or if you want to look at streaming. But if you want to be able to bring this chat in, what you're going to want to do is click on the three dots. You're going to go to pop out chat. You're going to take this link up here in the browser, and you're going to do Control C. And you can see I already have one set up, so you're just going to give it a name, and then you're going to Control V. It's going to then populate that right here, just like how you see mine. Since I already had it set up, it didn't go and populate it, but it was already there. Now what we need to do is take this and bring it over here into our chat area. So we're going to find our source that we have for our chat, and I have mine labeled as YouTube chat browser source. So I'm going to right click, go to properties, and since it's blank, we're going to go and do Control V. It didn't go and populate it, but it was already there. Now what we need to do is take this and bring it over here into our chat area. So we're going to find our source that we have for our chat, and I have mine labeled as YouTube chat browser source. So I'm going to right click, go to properties, and since it's blank, we're going to go and do Control V. Hit OK, and there we go. So I'm going to type in here in the chat. I'm just going to say hi. To set up. So that size it. But I wanted to at least show you guys how to do the custom doc for the chat, especially for those of us who stream over on YouTube, because this is like the only way I've been able to figure a workaround to try. And if it works a lot easier and a lot better, I have no problem sharing it with everybody else and even using it for my own self. But anyways, if you guys are
rejection state, your Q rejection state will be in Q2 instead of B if I have an A, rejected. In Q3 instead of A, have a B, rejected. Either move left or right, that doesn't matter. Okay. So I For transition diagram for it, very good. And we have to give a tape structure. So tape structure, I can merge two, three things together. Okay, so instead of finding a transition all the places, this is my input. Right? So I'm going to ink, I'm going to take one step ahead, reading what each and every input until I reach a done symbol. So I combine all the steps together. One diagram for it, very good. And we have to give a tape structure. So tape structure, I can merge two, three things together. Okay, so instead of finding a transition all the places, this is my input. Right? So I'm going to ink, I'm going to take one step ahead, reading what each and every input until I reach a blank symbol. So I combine all the steps together rather than just having a transition to Q or Q not here, Q not here, Q not here, Q not here, and Q not here. Your tape is going to be the same and your transition is also going to be the same. So I just mix two, three steps together. I write it like this. I read all the input, reach the blank symbol. So once I reach the symbol, what I did, I move one step prior to my input. So I just move this step to Q Q2. I haven't written Q1 state. It's okay, fine. I move to Q2 step. In Q2, if the input is B, if the last element is B, it is in correct structure. So I am making a transition to Q3 state. Okay, so I can just draw a transition. Go to an accepting state. So here I can just draw the input is B, make a transition to Q3. In Q3, if the input is A, we are going right. If the last element is blank, I reach the last element blank, and I am going to check what is there in the left side of it. One step prior, if the input is B, the input should enter at AB. Right? If the last element is B, it is in proper structure. I am going to make one more left side move to Q3, and here I am going to check if the element is A. If the input is A, we are going for it, Q acceptance state. Okay, so the same case as the previous one, but rather than checking the first two elements, I'm going to check the last two elements. So when I'm checking the last two elements, reach till the blank symbol, go one step left. If the input is B, make a transition to Q3. In Q3, the input is A. You're going for an acceptance state. You can move left or right, that doesn't matter once you are reaching your acceptance state. And what will be your rejection state? Your Q rejection state will be in Q2, instead of B, if I have an A, reject it. In Q3, instead of A, have a B, reject it. Either move left or right, that doesn't matter. Okay. So I think we got a transition diagram for it. Very good. And we have to give a tape structure. So tape structure, I can merge two, three things together. Okay, so instead of finding a transition all the places, this is my input. Right? So I'm going to in Q0, I'm going to take one step ahead, reading what each and every input until I reach a blank symbol. So I combine all the steps together rather than just having a transition to Q or Q0 here, Q0.
Hello.
Here, Q0 here, Q0 here, and Q0 here. Your tape is going to be the same, and your transition is also going to be the same. So I just mix two, three steps together. I write it like this. I read all the input, reach the blank symbol. So once I reach the blank symbol, what I did, I move one step prior to my input. So I just move the step to Q. Then we are going. So I can write. So here I can just draw the final structure like this. The entire tape, A B B A B blank blank, and my Q3 focus on this step, right? Q accept. One step left, and we are going for an acceptance state. Q0 and right A, is Q2 and for right side. And in Q0, if the input is B, move one step right. So I have merged a lot of steps together to reach this place. Okay, so this place transition is blank blank. So here my tape also remain as it is, transition also remain as it is, but I merged a lot of steps together, so I can use an asterisk symbol. So what is the meaning of this asterisk symbol here? Asterisk denotes it is a clean closure. With 0 or more move, I am taking from this step to this step. From this step on, with the multiple possible moves, 0 or more moves, I am able to reach this step. Okay, so you can write it like this. And this is the instantaneous description for this. And for this, the instantaneous description is A, B, B, A, Q2, B. You have the blank representation. And from this, I am able to do this. It is A, B, B, Q3, A, B. You have Q. So I here is what are the states you have? Q0, Q2, Q3, Q accept and Q reject. A finite set of states. And your inputs are made up of A and B. And the element that can be written in my tape is, what are the element that can be written in my tape here? A or B or blank symbol. Okay, and there is your transition function. You can write your transition function for anything. Q0 when the input is A. You have to write everything. I'm just writing table. What all states you have? Q and your table Q0 standing Q.
And actually this is quite a twisted one. Here the machine has to accept all the odd numbers, and when it is expressed in binary, what does this actually describes is when you are expressing any of the binary number. For example, when it is starts with 1, then binary equivalent is 1, and when it is 3, it is 1 1, and when it is 5 we have 101, I think so. Yeah, 101 to represent it. And when it is 7 it is 111, and we have all the binary values like this, and all the binary inputs the last digit is 1. So we are going to accept an input if it is made up of zeros and ones, and if it end with 1 then we are going to accept the input. So that is the one, this, and all the binary inputs the last Turing machine. This is a bit easier one, and actually this is quite a twisted one. Here the machine has to accept all the odd numbers, and when it is expressed in binary, what does this actually describes is when you are expressing any of the binary number. For example, when it is starts with 1, then binary equivalent is 1, and when it is 3 it is 1 1, and when it is 5 we have 101, I think so. Yeah, 101 to represent it, and when it is 7 it is 111, and we have all the binary values like this, and all the binary inputs the last digit is 1. So we are going to accept an input if it is made up of zeros and ones, and if it end with 1 then we are going to accept the input. So that is the only twisted thing that over here. So now this is very easy to construct it now, right? So we have to find the last digit, and if the last digit is 1 we have to accept it. So here, as per the Turing machine rule, we know Turing machine contains infinite tape as a memory unit, and whatever is the input that is written from left to right, and the tape is split do some cells.